All right, so it has been about 5-10 minutes since I finished the stream, and it was about 2 hours of it. And I had to make this mistake sooner or later. I hadn't hit record at the beginning, so we have no recording of the stuff that we just did. So I'm feeling like a complete muppet. So what I'm going to do is I'm going to go for a brief kind of overview of the stuff we did today and how we broke it down. So it'll probably end up being a little bit more coherent, and we haven't worked out everything, but this is what we got up to. So the general idea was we were going to look at Perlin noise. We were going to take the function apart and just try and get an idea of how everything hangs together. And let me switch over to this machine so I can control what's going on properly. And we started off by looking at just what Perlin noise is. And that it was a kind of gradient noise. In fact, I believe it was the first example of a gradient noise. I think it said down here, first known implementation of a gradient noise function was Perlin noise. And so the features of like gradient noises and Perlin noise pretty much defined by this. So the idea is that you create a lattice, a grid, and then at each corner of the cells, we're going to create a random gradient. And then the approach apparently is to take the for the point that we are at inside that cell. I'm going to have to draw this in a second because it'll make more sense. You dot product the gradients with the vectors to that point, and then you do some interpolation of those dot products, and that gives you the noise that we see in the top right. So to run through steps, we have let's just switch over to the doodle mode. We have a bunch of grid cells, and then we have a point within that cell, and for that point we're going to work out, let's do this in a different color actually because it'd be easier to see. We're going to do these vectors, which are called the difference vectors, and then we'll have some gradient vectors which will be randomly chosen, so they could be pointing anywhere for each corner. And we're going to dot product these things together, and then we're going to interpolate, oops, that one will go out to here, right? We're going to interpolate the dot products for each corner, and that's going to give us the value for the blue point right here in Perlin noise. And the advantage of this noise is it can be stacked up very easily. We just kind of add together different octaves. You take the Perlin noise function, you sample it at different frequencies, and you add those together, and you get the kind of effects that we're seeing up in this corner. But what's really nice about it is the size of the features, the kind of detail that we're getting, are all the same size, because the size is defined by the size of the grid, so that we can take bigger grids and smaller grids and add them together, and that's how we get that control over this otherwise fairly random process. Let's start looking at the code, because that's always better. Oh man, it feels like such a muppet. I can't believe it was really stupid. The reason was, last time I had to edit the beginning of the video because there was a 10-minute chunk at the beginning, the pre-stream, that I had to edit out, and I was feeling lazy, and I thought, oh, I'll start streaming, and then when it comes to the hour, I'll just start recording, and that'll be fine. And we'll have just the video to upload at the end, no editing. Of course, I didn't hit start. I go, muppet. Right. This function is already, once we've been through it, it was a bit more terse and a bit more named. It was named very differently. So these are my own names. So if they're inaccurate, I'm sorry about that. So what we're going to pass in is a point. Let's have a look here. Why are we not doodling over here? Let's try this again. Oh yeah, here we are. We're going to take this point, which is this guy here, and then the first thing we're going to do is we're going to floor that number and call it the grid coordinate, and that's going to be this point right here. So that's what we get. If we floor this, we're going to get this. And now we want to calculate two vectors. and they are the distance vectors, the green ones, this top left one and this bottom right one. I'm going to actually rub some of this out. Tell you what, let's do a bigger cell, because this is going to get a lot of writing on it, so we probably want something that's a bit easier to see. So let's take our nice big grid cell. And we had a point. That was the first thing we had, right? We have a point, and then we floored it, and we got this point, which is our cell number. And remember that last week when we did hashing, those hashing functions wanted integers. So they were mapping the whole integer space into a float between 0 and 1. So this is going to be handy. This we can use as the seed of our hash function, which is cool. And now we need the difference vectors. Really, we need them for each corner, but what we're going to do is we're just going to generate, oops, I'm in the wrong place right now. We're going to generate this one, and we're going to generate this one. And the way it's been done, okay, this implementation, the original in GLSL, was done by Brian Sharp, and he was the same chap we talked about last week who broke down all the hashing functions so well and showed us all these different things. So those articles are still fantastic. I'll put links in the doobly-doo, and yeah, check those out. They're way better explaining it than I am, but it's nice to take these apart. So what he does is he takes the XY, he takes the position from here, and he stores it twice in a vector 4. And then he subtracts this grid coordinate, the integer version here, whoop, and the grid coordinate plus 1, which is going to be this one down here. And so by subtracting those, we get these two vectors. So the xy here is going to be this vector, and the wy is going to be this vector here. And I've called them TL and BR, so top left, bottom right. That's just from what made sense for me. Also, I needed a short kind of name because we're on a stream and we only have so much real estate with the resolution and font size we have to use for this to be visible. Okay, so we've got those things packed into a vector. What's next? Right, so we need random gradients for each corner, right? That was one of the things we mentioned. So there might be a random gradient going this way, one might going this way, one going this way, one going this way. And the way we're going to do that is we're going to call our hashing function. Now this is a particular version that returns two floats, two numbers per corner. So for each corner of the grid that we're sampling across, it's going to return two floats. And that's perfect because what that gives us is an x and a y. We can use those as x and a y for our gradient vectors. So what he's done is he uses hash x and hash y are between 0 and 1 each. So the first thing he does is he subtracts this 0.4999 for each. Don't know why it's not 0.5. Like, someone probably can explain that to me, but that'll be a good reason. And that gets, so rather than a number between 0 and 1, now we've got a random number between minus 0.5 and plus 0.5. That's cool. So that's in grad x and grad y. Now these are vectors, remember. So this is a vector of x's and a vector of y's. So grad x, let's just call that gx over here, is going to have 4 x's in it, 4 x coordinates. They're like the x coordinate for this vector, for this vector, for this vector, for this vector. So 1, 2, 3, 4. And then grad y is going to have the y components of our vectors. And the reason they're packaged like this is that on the GPU, an operation on a vector 4, on a vector in general, is the same cost as an operation on a single float. And in that case, we want things to be fast as possible, so we may as well pack things together in vectors and do 4 things at a time, rather than looping or something like that, which is very slow. Branching in general is very slow on the GPU. So each pair is going to constitute one gradient vector. So these are our vectors that we've got at the corners. Cool. And now he does something quite smart. He multiplies the grad x's with themselves. So x1 is going to be multiplied by x1, x2. So each of these are getting squared. x1, x2, x3, x4 are getting squared. And we do the same thing here. The y's are multiplied with themselves. So these all get squared. And then he adds them together. So now we've got x squared plus y squared, x squared plus y squared in a new vector. And then he takes the inverse square root. Now I got myself confused here because in my head I was thinking inverse. What's the inverse operation? And I'm thinking the inverse of the square root, which is square, right? That's a really, I hadn't thought it through. It was quite dumb. What an inverse square root actually is if you have the inverse square root of x, so let's just say inv square root of x. What that actually is you take x, you square root it, so it's the reciprocal of the square root of x. Is that right? Is that the correct terminology? Maybe. It's 1 over the square root of x. So, when he's doing this on a vector, all these have been multiplied and added together. Now he's taking the square root of each one of these, it's component-wise. So we've squared them and added them together, which gets, when you do that to a vector, you get the distance squared. And then takes the inverse square root, which is going to be 1 over the length of each of these vectors. Let's see if I can just clear this for a second. So like x1 squared plus y1 squared, all square rooted, and then 1 over that. That is what is in the x component of this. And then we've got exactly the same thing for 2, for 3, for 4, you get the idea. And all of these are now stored in this vector 4. So we've got a vector of 1 over the length of each of the gradients. These gradients here, remember, these vectors. And that's cool, that's going to be useful again in a minute. But we'll put that aside, and then we're going to look and check it again to make sure I'm actually recording this time. And then what happens is we get down to here. And so we're back to this vector again, which remember stores this and this. This one in the xy components of the vector, and this in the zw. So what that means is that, okay, so this is, let's do this in a different color again. Oh man, I just don't have many colors. Yeah, let's do it in this. This is the x component. This one is the y component. This one is the z component, and this one is the w component of, where are we? This. So then he packs a vector 4 with xz, xz. So that's the x components of this. So it might be, in this case, 0.3 minus 0.7. So it'd be 0.3 minus 0.7, 0.3 minus 0.7. That's going to be in the first vector. And then this one, we're packing the y and the w components together. So this looks very similar. 0.3 minus 0.7, 0.3 minus 0.7. And that makes up what we've got here and here. Then that's multiplied with the grad x's again. So he's doing this and this multiplied by these. Now it took us a minute to work out exactly what was going on. It took me plenty of minutes to work out what's going on here. This packing is, what he's trying to do is he needs the distance vectors from every corner, right? He needs this one as well, and this one. But if we've got these two, then we've got all the information we need to construct the other ones. This one is just xw, and this one is zy. And so he packs these things together here and multiplies with this gradient. So this is multiplied by this is multiplied with this and this and this. Should be able to see where this is going. These are the dot products that were mentioned in the Perlin noise implementation in the Wikipedia. We're going to dot product the distance vectors, sorry, the gradient vector with the distance vector, And again, adding them together, and the dot product is the sum of all the components. And then by multiplying by 1 over the lengths, he's dividing by the lengths, right? So if you have this is where I get a little hazy. I'm just going to say I accept the fact that he's scaling these ones back. But what we've essentially got here are these dot products at this point. We've got some dot products, it's good to go. And they're scaled to get them into a certain range. And the range that they're in, see, we've got this multiply down here, and it says, this is a comment from the original code, which says, scale things from -1 to 1. And then we have this factor here that's applied component-wise to each of the things in this vector form. That was a little confusing at first, until I was thinking about what's the kind of the worst case, what's the maximum length any of these values could be. Well, it would be, for grad x and y, it would be that both of these hash functions returned 1. So it was 1, 1, in which case it will be scaled to 0.5, 0.5. And if you have a vector that's 0.5 this way, and 0.5 that way, then the length is 0.70 something. In fact, let's just work it out. We'll go here, we'll say vector 1, 1, and then we'll say the vector 2 length of that last thing is, is 1.414, which is the, oh yeah, it's not 1, 1, sorry. We worked out a second ago, didn't we? That the longest it could be is 0.5, 0.5. See, I haven't quite learned this yet, but we're getting there. 0.7, 10677, which if you multiply by 1.444441421, whatever it is, 0.7 multiplied by 1.4 gets around about 1. So this is the scaling. We took the worst case, worked out what I have to scale it by. So that at least makes sense to me now. Like, why that magic number? That's why that magic number. It even says here 1 over square root of 0.5, but I wasn't even seeing that, didn't tell me at first. I guess because I'm new to this. Why 1 over the square root of 0.5? But that's fine. That's what we've got here. And okay, so we have our dot products stored as a vector. So maybe we clear some of this stuff off now. And at least clear this space, so we have something we can work with. Okay. So we have a vector called dot products, and inside it we have dot product 1 and dot product 2 and 3 and 4. God, I write worse than doctors do. So that's packed into this here. And now something interesting happens. Now it wants to blend them. So we know from the Wikipedia article, after calculating the dot products, you're meant to interpolate between them. And this was done in a slightly odd way. And so you took a quintic curve, which we're going to have to visualize, because that's just, like, off the top of my head, what does quintic look like? So he gets this curve based on the xy that's in UV, so basically this in here. Takes the quintic of that and then blends that with, he packs this vector here with that value and 1 minus that value. So let's just take a second to actually look at quintic and see what's going on there. So if we come down to our fragment shader down here, let's go and say graph quintic over UV. And it's complaining here that there are multiple definitions of quintic. Which one do I want to use? So I have to give the type, which is float. Then we can get rid of that. Warning. Okay, so this is what the quintic curve looks like. That's good. Now 1 minus should look like the other way, right? But we don't have to imagine things. Let's go and actually draw them, because we can. lambda x float, let's put a space here for convenience, quintic of x over uv. Does that work? Yes, good. And then we're going to draw a second graph, which is 1 minus. And naturally, this is what we'd expect to see, right? We've got the second curve here. So this obviously is what he's going to interpolate using. And I guess, like, because we have distance vectors from each side, we're going to want the complementary. So as one goes down, another one goes up. That's going to give our weighting. He's trying to pack these into vectors so we can do a bunch of things at the same time. So then, what's interesting is, okay, so this is going to be x and y, which is this curve here. Let's write that down so we don't have to use our memories. So in blend 2, I think this is blend 2 dot x and y, and this is blend 2 dot zw. Like, that's roughly what's going on. We've got 1 minus each in each one. We can think of it as x and z. So when he does zx, zx, it's alternating values between the two curves, and then ww, this one, yy, from this one. And then, so what happens when you multiply these curves together? What do we actually get? So that's a behavior again we can easily draw. So let's go down here, and we're going to multiply. Well, that indentation was a little confusing. I should have checked that. Quintic by 1 minus quintic. Remove that plus because we're not actually using it at this point. And this is what we get. In fact, let's. Why am I removing that? Let's graph all of them. Quintic, 1 minus quintic, and the multiplication of the two, right? So now we can see how they affect each other. So we're going to get some kind of ramp. That's the overall behavior. We're going to have some kind of distribution, and the way we're packing these together is going to be used to blend each other together. So, and then we're doing a dot product between the values we calculated earlier, the ones we want to interpolate, and this composite blending thing, with like this blending vector we've got down here. And what that's doing is it's taking each component and multiplying it with its respective component. Take each, so x from here will be multiplied by x from here, y from this one into y from this one, z, w across the two, and then summing them all together. And that's our interpolation, and then sum, and that gives us the final value for Perlin noise. And so when we get rid of our graphs again, what we should see actually is if we let's not get ahead of ourselves here. Let's go and call Perlin noise with UV. We see this, and I'm going to multiply because we can't see much detail here. I'm going to sample the function at a higher frequency and remap it into a sensible range. This is our classic Perlin noise, and that's what we're getting from this function. Now, can't say I wouldn't write this function myself because I'm not at that place in my learning yet. But like with the hashing function, I feel like I can see somewhat of the pattern. You know, like this is roughly what we're doing with gradient noise. We're setting up gradients, we're finding their contribution to a point, we're interpolating the things based on that. Yeah, it kind of makes sense. I feel like going through this a few more times will probably be quite revealing. So this is where we got to with this stage. And then what we did was we switched over to, I had a toy that I was playing on during the week. And that was, as I couldn't go into reading how this function worked, because we were going to do that on the stream, I just decided, oh, well, we'll play with the function instead, like, and just see what we can do and actually do something with it 3D. Because, I mean, looking at the textures is nice, but not super interesting after a while. And once again, I'm going to just restart Lisp, not because we need to, but just because I don't trust the demo gods. I want this to work, seeing as we're actually recording it this time. What a kicker. It's a real shame as well. We had nice, great folks in the chat. Really cool to get the contributions. And one of the things we did was definitely just completely driven from there, which was we played with geometry shaders as well, and we'll get to that. Okay, let's pull this over. Now, this is going to take a few seconds of fiddling. Oops, where is the code? Right, I'm going to comment out this for now. This is something we did in the stream. And we've already commented out that pipeline, so that's good. Okay, let's see if this is going to work. Okay, we're going to reset the data, and we've got some terrain. Now, the way we had this originally was like this. Okay, so this is how we started off. And we went through a quick tour of the code. Now this is the rendering code down here, and so we're not going to spend time on that yet, because that's where we're going to do most of our time. So up the top here, we have a variable storing the mesh stream. This is the stream of vertices we're actually going to be drawing. Right now it's set to, it was set to nil initially until we called reset data. We'll see that in a second. We've also got an object that represents the model space. And this is part of a library called Keppel Spaces, and it allows you to create a graph of spaces, declare how they're related to each other, and then query the graphs. You can say, hey, what's the transform, for example, between model space and world space? In this case, it's not super interesting because it's identity. But you can also set up things to be camera spaces and then transforming between those, and it starts getting really interesting. And the eagle-eyed among you will see that we actually have model space in our GPU function here as well, which means we're able to use these spaces in our shader code, and I'll talk about that in a minute. So we need to populate this, so we're going to skip right down to the bottom of the code. All this code for doing what we're going to see was about 111 lines long, 107 lines long, something like that. Wasn't very much. We've got our little main loop here. This is a macro that gives us a main loop easily. And every loop, it's going to call step height map play, which is up here, and we'll visit in a second. Reset data, it looks to see if mesh stream's already defined. That's the variable from the top we just looked at. And if it is, it frees it. Frees all the data in there, because we're going to recreate it. And then it's going to call this function, lattice GPU arrays. What this does, it returns, it gives you the mesh data for a grid. So it's going to give you, in this case, a grid that's 100 wide and 100 deep, and is split up into 1,000 by 1,000. So this thing we're seeing over here on the top right is this, but split up 1,000 in each direction. The reason I do that is because we want to deform it and we want it to look nice and not too jaggedy, and we can afford that, so why not? Then we take that data and we create a buffer stream out of it. So we've got two arrays on the GPU. One is the vertex data itself, the actual points in this grid. And one is the index, which is saying which points make a triangle. So the first three numbers in the index array specify the first triangle, and it indexes into the vertex array. This is standard GL stuff, just with Keppel names. This is essentially what we're looking at here is two chunks of data in a VBO, and this is a VAO with some extra information for those GL people there. That's what's going on. And we stick this in mesh stream and we reset the camera position, which is just putting it where it is now. And then we were talking about step height map play. So this is what's done every frame. And this is, again, not too much here. It's a bit ugly because I need to my input library is pretty naff at the moment and it needs some work. It's just saying, hey, if the W key is down on keyboard 0, then take the camera position and then add the current camera position, and we take the rotation of the camera and turn it into a direction, so that's going to be a vector, and we're going to just add that vector to our current position, scaled by 0.2. And the reason we do that is to make it a bit slower, so we can see here we're going moving in and out. That's being controlled by the W key and the S key. Before we did the scaling, we were moving way too fast and it was super annoying. So that's that. And then here, all we're doing is saying, hey, if I've got my mouse button down, see, nothing's happening at the moment. If I press mouse down, I've got this terrible look camera. Terrible because wherever I click, it snaps to that rotation. It's really janky. All it does is it gets the normalized mouse coordinates, which is 0 to 1, 0 to 1, and makes some quaternions for rotating around the y-axis and the x-axis and multiplies them together and sets that the rotation of the camera. The camera's rotation is specified as a quaternion. It's simple enough to do it that way. Then, once we've got our control system out of the way, we have the actual rendering. And so we're saying as frame, which is a macro. As frame is very simple. Like what it does is if we expand it by doing this, I'm hoping this comes out on the stream. You know what, let's rearrange our panes a little. Let's just do this. And we should be able to see it now. This stuff inside the as frame is just put here. And then as frame does a clear at the beginning and a swap at the end. And then this other stuff is just to make sure that the right value is returned and stuff like this. But this is essentially all that's happening. We're doing clear and swap, and in between we're doing this stuff. So let's look at that. The first thing we do is we check to make sure that we have a mesh stream, make sure that the data's been initialized. And then when that's true, we say we're using this camera. And the reason is when we're drawing, we're going to transform all our vertices from world position or the model position. Yeah, but that's how it actually happen. We're going to transform from model position, the model space, through world space and to camera space. And it needs to know which camera space, because you might have many cameras, it's using. So this is informing the Keppel spaces system, which camera we're using. That's good. That isn't going to make much sense right now, but I will try to explain it a little later. Really, it will be the subject of another video because there's quite a bit of stuff. But anyway, we're just saying we're using this camera. And when we're using that camera, we're going to map the mesh data over this pipeline. And we're going to pass in this data as uniforms. And the only thing we're really interested in here is, hey, that's that model space from earlier. We're passing a type that's not a native GLSL type up to a GPU function. It's kind of strange. Let's go to draw a height map play, which is up here. And now we're finally up to where we're drawing stuff. Quick recap, GPU functions are defined with defun G and otherwise look quite like regular Lisp functions. Like Lisp functions, you can call GPU functions from other GPU functions. Or when you're defining a pipeline, you can specify that one of the functions is going to be used as a shader stage. Whether it's, so in this case, this one up here is being used as the vertex stage, and this one here is being used as the fragment stage. And what the vertex stage does is it takes the vertex data, it's going to do some transformations to it, we'll look in a second. It passes it on into the fragment shader with a normal, and then what's happening in the fragment shader is we are going to take an imaginary light position and normalize that, a light direction, the vector going to the light. We're going to dot product it with a normal, so we get some kind of contribution. We multiply it by a color, in this case gray. Yeah, we can mess with that later. This is why light and color are both in quotes, because neither of these things are very accurate terms. And then we add on, potentially add on some kind of ambient light, but we're not really using this component now. Let's just remove it. Cool, that's recompiled. And even though we can't see it, it's taken effect. Okay, so what are we going to look at next? So what we do to get our position for our vertex, we take the current position and we add on the result of calling Perl3. So what's Perl3? Perl3 is just a function that calls Perl1, this Perl function up here, and turns it into a vector 3. So all we have to think of is this is getting turned into a vector 3, multiplied by some scaling factor, added onto the position. So we're displacing the position, because its current position is this. All of the grid is at 0, 0, 0. Is at 0 height, and their respective x and y, xz coordinates. We want to displace this. So for example, what we could do is up here we could say, we're going to take the sine of the x of the uv. Now it changed a little, but it's not very visible what actually happened there. So let's multiply the uv by a larger number, so we'll see a bigger effect. And a bigger number than that. Okay? And here we can see what we're doing. We're returning a float. It's getting turned into a vector 3 where the y component is that float, that height. And then we're displacing the original position by that new position times some scaling factor. Because originally, if we do this, it's a bit small. Maybe we don't want that. Maybe it's a bit too small to see. We want shiny things for our stream that we don't then record. So this is how we're going to get our position. And now what we can do, rather than doing sine, which is kind of boring, we could do Perlin noise of the UV. But it's not called Perlin, it's called Perlin noise. So we Perlin nous. Yes, that man has nous. Right. And it's hard to see if anything's going on again, so we're going to sample at a higher frequency. And now we're getting somewhere, right? We've displaced some stuff, and we can actually see more obviously some of the things that we were talking about earlier. Hey, it looks like our texture again. We can see that each of the features are roughly the same size. That was like defined by our grid, right? That was one of the useful properties. And it's useful because then we can start sampling at different frequencies. So that one's kind of nice. But it would be good if it was times to make it a bit bigger. Maybe that's a bit too much. Let's do 3. All right. And then we're going to add it with that higher frequency one again. Let's do 8. And we're not going to multiply it by as much yet. That's way too much even. Let's do 0.4. Okay, maybe that's okay. And again, we can do higher frequencies too. Yeah, all of this is a bit gross, but we get the general idea. We can take sample function different frequencies to get different octaves of noise, and we can then add it together, and that has very controllable effects. You'd think after doing this stream once I'd be better at this. So that's the general idea. Now we can play with this in 3D, that's kind of cool. But what's interesting is obviously if the normal was just up, we wouldn't be able to see any definition because we wouldn't be able to calculate any shadows. So we need to get a normal vector. All right? So how are we going to do this? We call the pnorm function, which is up here. And it calls this function, passing in our function from here as a first-class function. This is one of the advantages of doing this stuff from Lisp. We get some of these things we built into our compiler already. So let's go and look at simple sampled normals. Here's the one that we're using. We're not using this one. This takes vector 3. We're doing one that works over 2D. And what it does, let's get the doodle up again. Doodling. Is that it takes the position we're at, let's say we're here. It's then going to call the function, our Perlin noisy kind of fractal noise function, and it's going to call it here and 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 here. Let's make that a 6. Why do I have problems with 6s? And then it's going to do a bit of math, basically doing differences in various directions, and to compute normal. So if that was over here, we're sampling here and here and here and here and here and here and here, and we're ending up with a vector that points in a direction. That's it. And this is nice because we can pass in a function as a parameter. This is going to generate the GLSL that we want without having to inline that stuff ourselves. Cool, so that's how we get our normals. Now there's a bit more jiggery-pokery down here, and this is where our model space comes back in, because when I had finished I guess the first real iteration of the compiler that I was starting to feel happy with. I was starting to write some shaders, and it was cool, but given that I put all this time into a compiler, I felt that, you know, this should be able to do things that you can't do in normal GLSL. I need to be able to extend this to do something cool, because otherwise, like, what was the point of doing all this? Other than to have the syntax, which I do like, not switching syntax and just switching problem space was nice. That was a good win for the compiler. I needed more. So one of the things I was screwing up all the time was that when I was doing manipulation of vectors in various spaces, like, hey, you're going to do lighting, but you want to do the lighting in clip space because of, you know, floating point resolution, and then you want to transform that back to world space and do this in world space, and then pass it along to the fragment shader. I was very often messing that up. And so what I thought it'd be cool is if you could define the space you're in, and vectors created in that space would belong to that space. So this is what we see here. So we have a spatial vector, which is created very like our regular vectors. But this vector knows it's in model space. It's statically analyzed that this is in model space. And when this value leaves this scope and enters clip space, the compiler is going to add in, it's going to add a uniform that's going to provide the matrix between model space and clip space. And it's going to use the graph of spaces that were declared on the CPU side to get the matrix, which will then be uploaded. And in this case, it's kind of trivial because, you know, it's one matrix multiply. I mean, what's the big deal? But when you start messing around with dozens of these in multiple spaces in one shader, it can be quite nice. It's not there yet, but one of the things that made me happy is all of this feature is defined as a set of macros and functions in a completely separate library from Keppel, from Vario, the compiler itself. So we're able to do something quite complex just with the fact that Lisp is extensible, and thus the compiler and everything is extensible. So all that happens here is we create a vector that we say is in model space, and then we allow it to flow into clip space, and it gets converted. And then that clip space value is what's passed on to the fragment shader. We would normally do this with the normal as well. Like if the normal was packed in with the vertex data, we would do this exact pattern here as well. But there's no need because we created the normal in clip space already. We created up here from our data, so it's already in the right format. And so when it gets down to here, we have our color that isn't a color. So if we wanted to, of course, we could go and change this to something else and make it a disgusting green. And that would be cool. But at this point, we're generally getting the idea of what's going on. And then, a wonderful someone, who was it? Was it Pom de Pim? Or was it Darius? I can remember your name now, Darius. I'm getting this. No, it was, who was it? It was someone who also had baggers in their name. Bore baggers. That was a surprise. What's the current story on geometry shaders? Anything cool you can show? Okay, so it was just like, where are geometry shaders? And the answer is they're working great. We have support for geometry shaders and tessellation shaders. And so what we did is we took this and we decided we were going to draw normals for every point on this surface. And so this is the vertex shader that we had before, and we renamed it, and we don't pass along the UV because we don't need it. We only need the position and the normal. And then our fragment shader is just going to be make it yellow. And in here we've got triangles, okay? That was the primitive type that was being used. And in here, what we're going to do is we're going to draw a line for every point. Let's get rid of some of this stuff. Remove that mouse. For every point down here, we want to draw a line to actually show what the normal is. And the way we do this, let's uncomment this code because it'd be nice to read. Is we have a function called genLine. Well, the first thing we have to do is we have to declare what the output primitive is. So in this case, The compiler knows what the primitive is coming in, because by default it's triangles. You can specify it to be anything you want, but default it's triangles. The compiler keeps track of the primitive flowing through the system, so you don't have to declare it again. You just declare the output, and the output is going to be a line strip, and the maximum vertices are 6, because in a geometry shader, unlike in the vertex shader where you're dealing with one vertex at a time, in the geometry shader you're dealing with the actual primitive. So we're going to get, in each invocation, one triangle. And so then we're going to draw a line for each triangle, and that's a vertex, a vertex, a vertex, a vertex, a vertex, a vertex, 6 vertices, that's the max. Then we've got a function called genLine, which is which point on the triangle we're dealing with. We have a magnitude, which will come into a minute. We have the original position, which is the GL position of the data that's coming in. Right, so I forgot to mention this, but a geometry shader, because it's taking the entire primitive, anything you return from the vertex shader is going to become an array of values. So we return one normal here, and this flows into here, but now it's an array of 3 normals, which makes sense, right? One for each point on the triangle. So again, we also get the GL position for each point on the triangle. We then add the normal scaled by the magnitude to this. So then we're getting this point up here. We had this, we've got this. And then we emit a vertex at this position. We set the position again, we emit another vertex, and then we end the primitive. And that's how we draw a line. And we say values here because we're returning void. We do 3 of those, and that's it. And so if I get rid of this, I was kind of nervous when I was doing this the first time because I didn't know if it was going to work, because this is the perfect time to find bugs in your code. Let's go and compile this, compile the fragment shader, compile the pipeline. You can see here, this is just us picking which GPU functions are going to be used as our pipeline, as our stages in our pipeline. And then we go down here and we're going to map the same stream over this pipeline with the model space. And when we do this, we get a whole bunch of normals. Now that's strange, they seem to be displaced. See that down there? Oh, I know why. I know why. Because we totally should have used the same, like the vertex shader here is so similar to the one up here that we should have just used this, because now this is the Perlin noise function that we made during the stream that I forgot to record. And sorry, this is the one, hold on, I confused myself. Yeah, this is the one we made during the stream I didn't record. This is the one we did just now, and they don't match. So we've got the normals for a different thing. So let's get rid of this. This returns a UV, which is a vector 2. I'm just winging it now because what we need are more problems. And it's going to be 3 vector 2s. Oops, sorry. And this needs a thing, UV. We're not going to use it. When we compile this, it's going to complain that basically the 2 pipelines don't match now. While passing to destructuring bind. Oh, I think I've made a mistake. No. Now that's actually an ugly error message. I need to fix that. Compile this. Okay, I'm just going to quickly check if we're still running. We are. If you do clear screen and it doesn't clear the screen, that means it's still drawing. It's not high tech, but it works. Right. So now we're going to go and say that the one that we're going to use is the geometry shader, that it takes a vec3 and a vec2, and we're going to change our vertex shader to be this one. And if all goes well, let's see. That's better. Now we open. So again, we're reusing GPU functions that we defined before in different pipelines. That's totally fine. Oh, that's odd. How dare you? Right. And now, if we can just get through the wonderful artifacts, right down here we'll see we have loads of normals. These are all the normals we've been drawing for every point. That's 1,000,000 vertices with normals. That's kind of cool. And they're a bit short. So what we'll do is we'll go over here and we'll change that magnitude. Let's put that to 0.8. Now they're longer. Let's put it up to 10 because why not? Whoa! Disgusting. Oh, that's gross. Oh, that's just foul. Anyway, that works. Oh yeah, I'm still typing over here. 0.4. Yeah. So that was, thanks to Borbagus for suggesting this. And straight away I looked at this and you go down and you kind of go, these normals, oh, I wish I could get a spot where you could actually see it. These normals are leaning in the wrong direction. So straight away, by visualizing this, we can see problems. Look at that, that's nasty. That's wrong. So I need to go and revisit that function. I'll do that probably after recording this. Okay, what else did we do? Oh, after that we went off ranting about the, basically some people got into a discussion on what they liked about Lisp, and for me it was that it's so easy to do things accidentally. And it's a very iterative place. And I gave the example of this, how the compiler started out was, you know, well, let's just do this again, because I'm quite happy to have the same rant a number of times. Let's bring up the rep. Something I think is really powerful is not just when you can provide good tools, but it's when you can show someone the route from where they are to where they want to be. They dream about doing something, say making a game. And if you put someone down just in front of C++ and GL, it's so daunting because you can't do anything interesting quickly. So you get your triangle up on the screen and it doesn't feel like, man, if I keep doing this, I'll have Unreal 4, you know? I'll have Battlefield, right? It doesn't feel like that anymore. It was so much easier when we were kids because you would write a text adventure, and a text adventure, even a bad text adventure, feels like a text adventure. It looks like a text adventure. It's just not there yet. You can see what you're doing and where you're going, and you can imagine the journey between them. Even though you're wrong, it's really empowering to have that vision of where you could be. And tools like Unity do this really well. You spend 5 minutes and you've got something that's a terrible game. It's not even a good toy, but you can see the vision from where you are to where you're going. And that's really cool. So for me, it was like, I didn't really understand what a compiler was when I started. And it's evident in Vario when A, it's designed badly. But B, the main function is called translate, not compile, because so I was just making a translator, you know? I was seeing, right, in GLSL, I was seeing this, vec3, 1, 2, 3, right? And I had, in Lisp, I could write this, vector 1, 2, 3. Well, how hard could it possibly be? Well, especially when you stick a quote in front of something, and now you've got it as data, how hard could it possibly be to transform one to the other? And so you start making a thing. And that thing is going to make a string. And it's going to be a function call. And it's going to have arguments inside. And for each argument, I know this is cryptic, but I'm speeding this up for you. Like, this took me a while when I was first learning. Something like this. And then I'm going to take the first thing from X and the rest of X. And then if I take that data I had and call thing on it, now I've got something that looks like GLSL. It's not. And I mean, at this point I might go, oh yeah, the only problem with it really is, you know, that it's the wrong case. So I call down case on it, and then now it's valid GLSL. You know, this is good. But what I really want to be able to do is write functions, you know, like def macro, maybe like def GLSL. That's what my macro is going to be called. And then it's going to take like a name and some arguments and a body. And then we're going to do the same kind of thing, right? We're going to make a string, which is going to have a name, and it's going to have this thing that we had before, these arguments. And even then I was bad at typing. Oh, wow. And I'm bad at copying as well. Let's do that again. going to take this, and then if I give it name and args, it's going to complain the body isn't used. So let's just shove that in here for a second. Let's go and put this on a new line and a new line, and new line and body, right? And then I can do def glsl, and I call it, it's going to be called main, and there's going to be no arguments for now. And the body is going to be, no, yeah, actually there will be arguments, it'll be x, y, and z, right? And then the body is going to be vec3 x, y, and z. Oh, look, it compiled. I mean, it didn't compile the middle bit because we haven't worked that out yet, right? But this outside bit looked like glsl. Oh no, we've got the same problem again, right? We've got to downcase everything. But now it looks a little better. And at this point, like, even though this is totally not the way to build a compiler, you're seeing from where you are and where you want to be, and feeling some kind of connection between them. And suddenly this starts looking more like, ever so slightly, like what you wanted to do. And this, I mean, this thing took me a week the first time I did it. You know, it's kind of, it's crazy now. But playing around with this is how I built the first version of Vario. And this is what I'm getting at, was the fact it was so easy to play with an idea. And then realize, hey, each of the arguments, like the argument can be, you know, typecase X, right? And it could be a list, in which case we want to do this. Or it could just be anything else where we can just return it as is. And we're going to do this recursively. Not because it's a good idea, but because we can. And already we start to get something, like, I can't stress enough just how powerful this is in a language. Not that people can do exactly what they want straight away, but that they can see the direction of where they're going. Right, I'm going to stop because otherwise I'll rant for even longer, and I've done that once already this evening. This to me was meaningful. And even now, like, even having done a better version of this, it's still so addictive to try and, you know, just poke the toy a little bit further. Just one more change, and it'll be a bit better. And that's so enjoyable. Anyway, that was that rant summed up somewhat. And then that kind of drew it to a good place to close, and I think it's a good place to close again now. Jesus, it's been a while. It's like been another hour since I finished streaming. Next week, I'm not going to do a tear down a function video. We're going to do just video on Keppel and Vario and things in general. So we're going to play with Lisp, and well, we're going to. Basically, I want questions. I want to know what people want to know. I've had some questions about how Keppel hangs together already. So wherever you're viewing this, leave me comments of what you'd like to see, and I'll try and get those into videos where they make sense. Thank you so much for watching once again one of these streams. And I'm sorry that I couldn't give you the real version, but I hope that this summary is okay, and I hope it has a little less blithering than the original one did. But anyway, that's enough for now. Take care, and I'll see you next time.